Hi, this is Giovanni Daprat speaking, and welcome to example 6. Hope you get a chance already to watch other videos, and feel free, if in case of any doubts or questions, to contact me anytime, and we can discuss. And actually, if you need the data that I use in the example, I can send it to you. So example 6 deals with water and oil flowing. This is there are actually is quite a common situation that probably you never find just oil producing. There is water and oil more common. Okay, let's go with the test objectives. In this case, is to identify the reservoir model associated to the well's drainage area and determination of reservoir and well evaluation parameters considering two-phase flow, water and oil. Actually, here you will see a PVT, so we have to use this concept of mobility, and we have to deal with relative permeabilities of oil and water, as we will see later on. Regarding reservoir and well data, you can see it here, the initial pressure, thickness, radius, porosity. Completion is a vertical well. And regarding fluid, you have an oil of 26, API 26, a salinity of 10,000, reservoir temperature. And once you got your value for the initial pressure, probably is something you have to find out from the analysis here, but there are many cases where you can have this information from formation testers. What I'm trying to say that you got your initial pressure or the pressure, um, the temperature, and you can get from correlations formation volume factor and oil viscosity, for example. Because as the other many other wells in these examples, this is an exploratory oil and water well. Actually, it is offshore, and I was also present and managing the part of testing and also the data interpretation. As with many other examples, this is what I mean sometimes what I'm telling you, the data is inspired on field cases, but not just field cases from the literature. I try to use field cases where I was present, so I have a better knowledge of what the situation was. So here we have the phases, the production. This is the water production, as you can see, is quite high compared to the oil production, which is this one over here. And this is the total production. Um, uh, these are the bottom hole pressures to tell you they were acquired with electrical submersible pump because offshore you cannot use you cannot you're limited, and in many cases when you realize that the well is not flowing naturally, you need to assist with a pump just for the test, I mean. So here we have two build-ups, build-up 1, build-up 2, where we're trying to get now extract information from the analysis and uh, to get to determine the parameters as said before. Well, we start with the classical log-log and semi-log diagnostic plots applied to, in this case, to both build-ups, initial and final. You can see here they're quite, uh, let's say, same tendency. So this is the semi-log. And here we try to simulate or to try to look of possible models to simulate the data. These two are presented here I should say I have another models I try, but the best ones were these two, which is an homogeneous leakage fault and a radial composite model. You can see here they're quite, let's say, quite, they simulate quite well the data. And if we do a zoom here, you can see here that both models actually, practically speaking, are the same. You need later on to see which one you're gonna be in love with or which one you're going to choose. Other than that, this is quite classical, like Welbo storage, let's say signature, transition, and then radial flow, and then there is this deviation here that could be uh, as a result of having a radial composite uh, reservoir or an homogeneous with leakage fault as a discontinuity. Okay, so results from these models are presented here based on the PBT. We use I'll later on, I hope to use the software so I can show you how to get these results using the Sapphire. Okay, in the leakage fault model, we have this result for the well and wellbore, mainly the skin and the what kind of wellbore model, wellbore storage model, and constant in this case. And here we have the boundary type. The reservoir type is homogeneous, and a boundary type like a leaky fault at about 200 feet from the well. And a leakage uh, of zero point 0.5. It's quite a conductive fault. And the results, when we enter to use the multi-phase transient results, you have your permeability for the oil and your permeability for water. In this case, the average water saturation is around 0.5, 51%. And this is data when you're dealing with two phases, like in this case, uh, water and oil. The radial composite model, these are the results. You will see they're very, very similar, practically speaking, almost the same. So, as I said, later on we have to choose which one makes, we have to integrate information to, to consider which model is representing the best data. So here we have a radial composite means that there is a change in the mobility of the faces at about 201. In the previous model, we know it's at 200 feet, there is a leaky fault. So mobility is not very close to 1, diffusivity half, 0.5. So, and here is the multi-phase transient results, permeability for oil, effective permeability for oil, for water, at this water saturation. Okay, we can see here that the pressure data simulation, we can use either of the models, the leakage fault or the radial composite. And basically, or practically, they're the same, and actually, both models simulates quite well the whole pressure test history, which is, as I said, in, it's a validation type of. Um, okay, so how about now using just one phase to analyze the data? In the past result, they are considering both phases, oil and water, but in many cases you're tempted to just use one phase. Um, and if you use that, you can see here the log-log plot of the buildup and the diagnostic, the signature having oil just oil based, the derivative based on using oil or only oil, and using both oil and water production rates. You can see here that there is a difference. You can note here, if you look at the derivative, there are some differences, not exactly the same. Um, it's but from a practical point of view, uh, it's not. You can consider that is it's okay the tendency for the derivative for both. Okay, so what we do now is let's do the interpretation just using oil as the production rate, and then we go ahead and we do the same that we did in the past using both productions, and you get the results. And for the simulation pressure test history, if you use that only, you can see here that even though it simulates very well the previous drawdown period, when you try to go back to reproduce the whole test history, there are a situation here which you can fix it. And a trick is to use skin dependent on time. And if we do that, we can have this simulation for the whole test pressure history. Okay, maybe one thing here is okay, if I use this only oil or only water in this case, you may say, well, but you have an important water production rather than oil. Uh, but in any case, if you do the analysis, just considering one phase, you can see here that even though permeability is in the order 70s, millidarcy 70, um, the distance to the leaky fault is not the same, and the leakage uh, value is not the same either. And on the top of that, we have to use skin dependent on time to simulate the data, which basically is a trick. So in conclusions, based on pressure transient analysis of the build-up data, both a leakage fault and a radial composite reservoir have been found to simulate quite well the acquired transient pressure data. Now here is, according to the seismic comment model, and this is a comment rather than a conclusion, a fault is inferred not too far from the well. Using an exploratory wells, you do have some seismic model to help you. Also, it may help you if the model is resolutive enough as to see faults. In this case, it can be seen clearly, and although the conductive nature of the fault cannot be determined via seismic model, it helps to consider the homogeneous leakage fault model as the interpretation model. As, this is the things in many cases, in particular with the exploratory wells, that exploratory well could be completed or could just be abandoned. But at this point in time, you need to integrate information from other sources. And in my experience, the seismic model has been a good one. And considering only oil as the producing phase, the derived values of parameters like the distance to the leakage fault, leakage alpha value are quite different compared to the ones derived using both water and oil rates. In addition, in order to simulate the pressure test history, a skin-dependent on-time auction was used. Okay, now let me go and I have here, let me bring here the software, the Sapphire, and let's try to reproduce the results. I already have them here, but just I'll show you a few steps on how was it done. So this is our what I showed you before, different colors. Okay, this is your bottom hole pressure. This is your rates, oil, water, and total rate. We have this build-up and this other one, so we proceed now to extract, uh, and we choose this build-up. We can use the first build-up here, or this one here. Let's choose this one here. And you see here I'm using production, total production, which is oil and water production. So I'll go ahead here, and I will help a little bit the software here. Um, we got tools like, let's see here first, before we go to the tools, I'll show you um, the leaky fault well storage constant, you can see here, and I will show you some you see this is the tool that uh, is available in Sapphire and helps you to define the flow regime. Remember, flow regime identification is very important because you will end up sooner defining your model. This doesn't matter if you don't simulate the whole pressure history. From recognizing this leaky fault, you can get already some results like where the distance of the leaky fault is, 189. Of course, it's not like that. It was 200. Here we're just playing and we have not do the complete simulation. But this is very important because there is always equations related to the flow regimes. Those equations, the parameters are related to these flow regimes. And actually, I saw many articles lately where you can use your radial flow signature or a fault signature, and and you monitor that in time, especially with permanent pressure gauges. Okay, so this one is gonna help you now because we're gonna run the model, in this case an homogeneous one. And let me take this out. And now I go to analytical. And before that, I'll go to PBT and make sure that in the analytical modeling, I use, in this case, we're going to use PRIN. If we go to numerical modeling, then we use the real PBT. But, well, let's go to analytical modeling, and here you can define what your water oil relative permeabilities are. I mean, you just set this, and if you got this information from other sources, you can enter here. So, and then you go and you try now, you already got an idea of what the distance to the leaky fault is, because as a good tool, the Sapphire helps. If you don't have that tool, then um, you can do it as I was doing years ago. Um, but that means that you have to be trained. So I'm like machine learning, I'm a human learning. Maybe during over the years, I saw the signature. I may have an idea of what that is. I mean, if it is a radial or if it is a leakage fault. So let's assume this and generate the model, and then you can see here. Then you do some improve. And here you have the results that are shown in the presentation. Maybe a little bit different because anytime you run this, especially improve, you may get a little bit different in the results. And then let's look at the multi-phase transient results here, where you got your permeability to oil, to water, and Other information is related here, reservoir and boundary. You have the distance to your leakage fault, the leakage alpha value, which is well, good conductive fault, and the reservoir type. So now if look at here, we're using both production of oil and water. Later on, I'll show you what happens if you just use oil production. So this is one model, and the other model that you can try now is you can go to back to, we can do like this, new based on this analysis one. And here we have you extract your delta P again, like here. And that helps a 5 here. And then now you make sure that from PVT we're going to use, you have to make sure to use this, and we already know that uh, we have it already, the PVT. So here now we're going to use the radial composite reservoir, and we go to getting some helps from the tool, which is a radial composite infinite. Okay, and here it's a matter of playing now with uh, radial composite means that you have an initial radial flow which is in the region close to the well. Let's say this is quite used for fall-off testing when you have a water bank which is displacing an oil bank, to make it simple. So if you compute mobilities here, they're related to the oil bank. And eventually here, you're going to what is the kind of a radial, let's say, flow for the oil bank. Okay, so if I do that, then you see results in plots, and then you're going to have, besides getting your water permeability, also you're going to have an idea that at 207 feet, there is a change in the mobilities of the faces. Okay, let's go now and try to simulate the same that we did with the other model. Going here, constant vertical, radial composite, compose. Let's just try post PSUV generate. And here we can improve a little bit. And here you have the, let's take out the tools. You have the solution using this model here. We can compare that solution with, well, in this case, we're not going to do it because I'm using the same, with analysis 1, we get, okay, analysis 2, I'm sorry. We can compare now what we did for the past and the last model. And here you can have both models, like is shown in the presentation. You can see here these are quite they apart each other, but basically from a practical point of view, both solutions are valid, let's say, from a mathematical point of view. And same for the simulation. Again, if we use only one phase, let's say we use only a production phase, oil phase, then we have to go all this way and oops, let's go ahead, and then Let's help here. Radial composite 1, 200, it's okay. Okay, let's 4 impose space will be okay. Generate. Let's go to improve. Okay, here I'm not going uh, to keep going. I did it already. Like in which the result is this one here, only using one phase. You can see here. So if we keep working on here, you're gonna end up with these results. So now you have this, and you realize that it's not reproducing the whole pressure test history. Then you can come here to the analytical, and then you go to the um, time dependent scheme. Here you can just say split steps, compute, and then you're gonna have here for each of the periods what is the scheme value. And in that way you get these results here. Okay, this concludes this example, the sapphire. Let's come back here now, and I would like to thank you for your time. Hope you enjoy the presentation, and again, please feel free to call me, or if you have any comments, you need the data to do yourself the interpretation, just tell me. Thank you very much.